Good. After we have been discussing the general framework, we will discuss now examples, so this becomes a bit more plausible and intuitive to you. The examples I'm going to look at are the following. I'll look at Brownian motion. That basically means I'm asking what is the description of a particle suspended in a fluid. So how do I describe Brownian motion? The next example will be what's called the Ornstein-Uhlenbeck process. What I mean by that is very simple. You put a harmonic potential. You can realize this by a laser beam. And in this harmonic potential, in this trap, you put a bead, so a colloidal particle, and you consider this colloidal particle to be subject to such a harmonic driving force. So it's driven towards the minimum, and it fluctuates around it because of thermal fluctuations. So you have a drive towards the minimum, but there's also random fluctuations that drive you up and down the potential landscape. And the third example is hemotaxis, and this means that you have bacteria that move in a certain direction, and they have a run velocity and a tumbling rate. And a tumble rate. And both of them are positions of space, because there's some chemical in the environment that determines how fast bacteria run or how often they tumble. And we would like to know what is the dynamics, the steady state of such a chemotactic problem. Good. This example here will be particularly important because what it will teach us is, given a stochastic process and knowing that we know the statistical physics, we can actually get some constraints on the coefficients that we have in our model. Okay, so let's start. Let's start with the simplest case, which is Brownian motion or the Wiener process. It's just different names. One is used more often in mathematics, the other one in physics. There's various ways now to start the analysis. One is, and that's the one I take, is to say I know the probability distribution, P of xt, conditioned on some initial condition, and then given that, I calculate the moments, the first, the second, the third moment, and I derive the Fokker-Planck equation. Okay? So let's assume that we know the distribution function. This is in general not what you have, right? In general, you don't know the distribution function. That's something you want to calculate. But here, in order to show you how these things work, I assume, and this is now in 1D, to make things simple, I know the distribution function for the transition probability density to be a Gaussian distribution function. So 4 pi d t minus t naught, and the exponential of x minus x naught squared divided by 4d t minus t naught. Okay? That's basically the definition of a Wiener process. That's the defining probability density for transitions And then we want to calculate the moments to derive the corresponding Fokker-Planck equation. And that's easy because this is just Gaussian integrals. So A is the average delta x over delta t in the limit delta t going to 0. That's obvious here, right? That there is no direction in a Gaussian distribution. Left moving and right moving is equally likely. So there's no, the Gaussian is centered around the origin or around x naught. So this is actually 0. There's no drift of our system. Okay. We can draw the Gaussian, and it's going to look something like that. For x naught equal to 0, if this is being x, and then the Gaussian just spreads out over time because the variance grows in time. The second moment is delta x squared averaged over delta t, and I'm sure you have done that calculation once before. This is just calculating the second moment of a Gaussian distribution, and that gives you 2D. You can also check for yourself that the higher moments, they all go to 0 in the limit delta t going to 0. That's quite straightforward to check, and I'll leave it to you as an exercise. Or you can also look up the lecture notes where this is formulated as a tutorial, and you guide it through the analysis. So that's now very, very simple, right? So the first moment is 0, the second moment is 2D. I have a one-dimensional problem. I'll just use the results I just got and rewrite my Fokker-Planck equation for this particular case. The A here that I have becomes 0, so there's no drift term whatsoever. And the second term, the Bij, is 2D. Delta ij, there's no higher component, so it's basically D. And that means now the corresponding Fokker-Planck equation is dx squared p of x and t, x0 and t0. And that should be no surprise, because in the end we're describing something that's a random walk, and what we get out is the diffusion equation. There's an important conceptual difference, though, to the diffusion equation. The diffusion equation is an equation for an actual density of many Brownian particles that evolve in time and in space. This here is the time evolution equation of the probability density for a single Brownian particle, and not the density of many Brownian particles. But still, because there's a non-interacting system, when you have Brownian particles that don't have pairwise forces, the two things are related. So what's the solution of that? I'm going to say, well, you have started from this as the solution and constructed a differential equation that should give that solution. So you can check for yourself. If you insert that into this diffusion equation, it is a solution. So you can just check by insertion that this is a solution. You can also more formally solve a diffusion equation by standard methods that you know. You go to Fourier space, you solve the problem in Fourier space, and you back transform from Fourier space to real space, and then you also get that. Okay? So that's not such an important point. All I wanted to show you is that there's this one-to-one relation between a Gaussian probability density and the diffusion equation. Let's now go to our second example. The second example is this particle in a harmonic trap. Let me go over there. So a particle in a harmonic trap. So that means our potential u of x is a half k x squared. That means I'm again just looking at a one-dimensional problem. So how would I set up the corresponding Fokker-Planck equation? Now I'll do this differently now. I will first look at the deterministic time evolution. What would that be? So you have this trap. Here there's a particle suspended in a fluid. There's a force coming from the harmonic trap. That's a linear force because you have a harmonic trap. And this linear force will be balanced by friction effects that you have in the solution. Okay, so as you drag a particle through a liquid solution, there's going to be drag, viscous drag, and there will be a balance between the harmonic force that you have here and the viscous drag. I don't consider inertia here because I think of the system as an overdamped system where all kinds of processes that come from momentum relaxation, they have already happened. So I only have force balance between viscous drag and Hookean forces. Right, so we have force balance. And this force balance means that my restoring force from the harmonic trap is given by the friction coming from the solution and this friction coefficient for a bead here, which has the radius r, and the surroundings has a viscosity eta. You can work out that the friction coefficient is 6 pi times the viscosity of the surrounding fluid and the radius of the particle. That's called Stokes drag. And this is the harmonic trap. So an elastic force driving it to the minimum. And that would mean, if I just have this, that my particle relaxes back to the minimum of the potential and game over. Nothing else would happen there. So I would have a dynamics x dot equals minus gamma x, where gamma, just collecting terms, is the spin coefficient divided by the friction coefficient. So you have exponential relaxation towards position 0. And that can't be quite right, because you know from equipartition of a particle in a harmonic potential that the mean velocity of that needs to be related, the mean square velocity needs to be related to the to kBt, and so needs to be the other degrees of freedom, like the positional degrees of freedom. Each of the harmonic degrees of freedom should have a correspondence in terms of kBt. Okay? So that can't be quite right as description for the system. So what we need to look at also is the random part. And for that, we just assume we have Brownian motion on top of the deterministic motion. And the Brownian motion is happen to be with a diffusion coefficient d. So what do we have? We have a drift a drift vector, and this drift vector is simply given by the deterministic part because it's the mean velocity of our process. So it's x dot. Right? Remember, a simply is the x dt, so the velocity x dot, and this is, I can read this off, minus gamma times x. For the second coefficient in the Fokker-Planck equation, I just assume that I have on top of this deterministic part Brownian motion with a coefficient d. Okay. A question you can ask yourself, we will answer this, is R, d, and gamma, are they related? Can I vary diffusion coefficient independently of the friction coefficient? Or is there some physical constraint that relates the two? Good. So let's write down the Fokker-Planck equation. The Fokker-Planck equation for that is dTp, xt conditioned on some initial condition, equals dx, and now you have a drift term, right, that's dependent on the position of my particle, so it's gamma x, and then I have the conditional probability plus a diffusion term dx squared p of the same arguments as all the other terms that we have. There's a partial differential equation, and you need to solve it. How do we solve it? I'm going to show you a technique which is very general and works for many partial differential equations. It's called the method of characteristics. And it's basically trying to map this partial differential equation into a simpler set of equations. Let's try. So we define a function which is the Fourier transform phi of k and t as an integral over x e to the I kx p of x and t x naught t naught. And now, as we have defined this Fourier transform, we're going to write the equation for that Fourier transform. Well, if you do the math, you do get that dt of the characteristic function plus gamma k dk phi of k and t equals minus d k squared phi of k and t. It's still a partial differential equation, but it's a little simpler now because instead of a second derivative that we had before, we only have a first derivative in the Fourier transform variable k. We have also an initial condition, phi of k at t equal to 0 equals e to the chi x0, where x0 is just the initial position of our particle that we consider. So that's the equation we need to solve. It's a partial differential equation. Still, it is, but it's kind of simpler. So let's make an ansatz Namely, I define a function phi of t. I know I should introduce another symbol, but let's use the same symbol. And I define that to be phi of k and t and t. Okay, so instead of solving the equation for k and t, I take t as a parameter and then try to span the solution manifold by going along one axis in t, and the other axis is then k of t. So let's see what this implies. We have this ansatz, and when I now write the total derivative of that, then of phi of t, I can rewrite this by the chain rule as the partial derivative of phi with respect to k, and then the time derivative of this function k of t with respect to time, and then the partial derivative of my function with respect to time. Okay. Now I can make a choice. If you compare this with the equation above, right, if I choose the time evolution of this function k of t to match the prefactor, so to be the same as k, a gamma k of t. So if that's my choice for the time evolution of k of t, I do get the right-hand side, because this is the differential equation it obeys. So this is then minus d k squared of t phi of t. And that means now we have two equations. We have the equation for phi, and let me reiterate the equation for k. dk dt is gamma times k of t. Right, and that's simpler. I have this equation for phi of t with that right-hand side, and I have this equation for k of t. I have two equations instead of one. That's the price I have to pay, but they are much simpler, and they are so simple that you actually can solve them analytically. Let's do this for the second equation first. Well, this is the solution is k of t equals k naught e to the gamma t, with k naught just being defined as the initial value of this function k of t. I can also solve the second equation, the first one. This phi of t, here is the initial condition, phi of 0. And again, this is just an exponential, but I now need to integrate. This is minus d, integral from 0 to t over some time t prime, k squared of t prime. And the initial condition here is phi of naught is e to the I k naught x naught. So I'm done. I can solve these two equations. By the way, the method of characteristic is called that way because this equation with that equation are the two characteristics of the partial differential equation for which I can give the complete solution. So taking things together, what I have is phi of t equals to the exponent I k0 x0, that's the initial condition phi of naught, and then minus d integral 0 to t dt prime k0 squared e to the 2 gamma t prime. Okay. So I'm inserting the solution of the second characteristic into the solution for the first characteristics. I can do the integral. This is not hard. This is the exponential of I k0 x0 minus d over 2 gamma k naught squared e to the 2 gamma t minus 1. And I can write this now instead of as a function of k0. I can also write this as a function of k of t. And then it becomes I e to the minus gamma t k of t x0 minus d over 2 gamma k squared of t 1 minus e to the minus 2 gamma t. So I wrote it in the form such that it matches the ansatz that I started out from. And now I do have a solution because this object that we calculated, I've written in this form, and that means my function phi of k and t is given by the exponent of the right-hand side. Good. Let me wipe the board. The differential equation for the characteristic function using the method of characteristics has been solved. And what we find is that this is e to the I, k e to the minus gamma t initial value of the position minus 1 over 2d, d over gamma, k squared 1 minus e to the minus 2 gamma t, average, bracket closed. Okay, so now this is a characteristic function. It's not the actual probability distribution. But if you have some experience, and I guess you do in the meantime, with characteristic functions, this is the characteristic function of a Gaussian. The first term here is the drift term. So this is I k average of x. And the second term is minus a half k squared variance of x. That then means, so this is the characteristic of a Gaussian function, and you can simply read off the mean and the variance from that characteristic function. So what we get is that the mean x equals the initial condition e to the minus gamma t. That should not surprise us because that's simply the relaxation of our particle that comes from the deterministic solution. So when we started writing down the differential equation in deterministic form, x dot is minus gamma x. The solution of this is e to the minus gamma t. And that's what you recover here as well. This corresponds to the time evolution of the deterministic dynamics. The variance of x is given by d over gamma 1 minus e to the minus 2 gamma t. So it's given by the amplitude d over gamma, and it converges to this amplitude because that second term goes to 0. This approaches as t going to infinity d over gamma. Now, the question I have posed this one, are d and gamma related? That I can answer now by the following argument. So this is what I get out from the stochastic dynamics. But what I must have is, so at t to infinity, the system should be in thermal equilibrium. Because after all, I'm just considering a Brownian particle in a given harmonic potential. In equilibrium, what I know to be valid is the equipartition theorem. That means every degree of freedom will on average have a half kBt as its energy. So that means a half k mean of x squared, that's the degree of freedom of the motion of the particle in the harmonic potential, has to be equal to a half kBt. Okay? But then you have to combine it with what we just found. This has to be the same as what you get from the calculation of the variance. So this d over gamma must be connected with a k. You just have to equate it to the corresponding expression. And that then means that the diffusion coefficient is not arbitrary, but it actually needs to be of this form. Okay. Given the friction coefficient, given a particle that you have, this is how the friction coefficient determines the relaxation of the particle to the minimum. If you multiply kBt with the inverse, which is the mobility, you need to get the diffusion coefficient. So relaxation towards the minimum given by friction is related to fluctuations determined by the amplitude of diffusion. This has a very famous relation. It's called the Einstein-Stokes relation. And it means that in equilibrium, the fluctuations determined by the diffusion coefficient are related to the friction, which in our case is the Stokes friction coefficient for a bead in a harmonic potential. So as a consequence of thermodynamic equilibrium being reached, the coefficients for noise and drift, they are not independent terms. They have to be related. Otherwise, the system would not relax to an equilibrium state where equipartition holds. Good. With that, I would like to stop for today and take your questions.
Can we start with the overlap condition? Can we already say that, like, are we already in close to equilibrium condition?
Now, overdamped and equilibrium are two different things. The question is, does being overdamped mean we are close to equilibrium? Answer is no. Overdamped just means that in the dynamics of my particle, the relaxation of momentum is much faster than other relaxation processes. So I can neglect the inertia term and write the equation of motion in terms of friction and of the harmonic trap potential. Close to equilibrium means something different, right? Close to equilibrium here means this is the parameter that characterizes how fast you go to equilibrium. The steady state is when this is 0, right? So it means the typical time to relax to equilibrium is 1 over gamma. So it's given by the friction coefficient, and this friction coefficient here, right, this gamma, is related to the stiffness of the harmonic potential and the friction. So you can make the rate of going to equilibrium faster by tuning the stiffness of your potential and by tuning the friction coefficient of your medium. Right? That's what determines the time scale. Yep.
Is this process equivalent to overdamped Longevian equation?
It is well, we come to that. That's a question you kind of asked too early because you don't know in this lecture anything yet about Langevin equations. But we're going to show that the Fokker-Planck equation that we wrote down here in this particular case maps to an overdamped Langevin equation. And then you can ask, given a full Langevin equation that includes the inertia, the damping, and the potential, can you formally derive the overdamped Langevin equation in a limit where momentum relaxation is faster than other relaxation phenomena?